statistical description of the sky at cosmological scale, please.
And some machine learning stuff. So first, I'll have to say that this is a very technical talk, but I'll try to give a taste for people who are in this audience, for especially people who are interested in observations and phenomenology, for the relevance of carrying out calculations, because this is something that more and more we are avoiding for a number of reasons. And so this is the first part of my talk, some actually rather trivial formulas, but that, as far as we know, were not known on the literature, that help us understand and describe large-scale structure as we observe it, which is in the past light cone, and not just in some ideal time equals to constant hypersurface, which is some construction we impose on the data. Also, I'll talk about some applications of machine learning just for fun, because it's something we do for fun. Everybody is looking at how machine learning can solve all their problems in life, and sometimes they do solve some things at some cost. So first of all, what we care about when we try to describe the large-scale structure of the universe. Of course, we don't care about the position of any particular galaxy. All we care about is the relative positions of objects in the universe, because that tells us something about how they initially formed, the initial perturbations, but also how gravity and other forces work to bring these objects together in these so-called structure formation, growth of structure. So we care about observing galaxies and their relations with respect, in their positions with respect to each other. That is what's going to tell us about the dark energy, nature of gravity, etc. So we map out the galaxies, and they have distances both along the line of sight and across the line of sight, and these are intrinsically different. The universe, of course, is homogeneous and isotropic, but as we observe it, which is in the past light cone, they are not isotropic, because along the line of sight and across the line of sight is different, for a number of reasons which I'll expose here. So we need to describe something intrinsically in the past light cone, which is something that people knew since forever, of course, since even from Peebles' paper, it's already in there. Many of the ideas that I'll be talking about, I'll just bring some formulas which give us an analytical description of what's going on, which is important. So I'll also talk about the statistical description here, which depends on not only on the covariance of these observables, which are these two-point functions, correlation functions, and power spectra, but also about this Fisher description. And why do we care about this? Because, first of all, you need to understand things in some analytical sense, not just to simulate things to death. And which is sometimes our, we have this instinct. We have near infinite computing power, and we want to simulate everything, but we need to actually understand what kinds of informations are being propagated into our physical problem, and we need to forecast the power of our experiments, and it's something that it's sometimes hard to do if you're just simulating things, if you make just a forward modeling of everything. If this is a kind of very costly approach. So what we want is to describe statistically this without trying to impose some sort of artificial volume into our observations, which assumes that there is no evolution in here. So we observe things on the past light cone here, and if we just draw a box and we try to do some Fourier transform of our field in here, we end up having to basically smear out things in some ways, which may not be desirable. So we don't want to assume that the sky is flat, so that we just basically assume that modes along across the line of sight are just basically just like Fourier modes, which they are not. So this is the flat sky approximation. We need to observe both the large and small scales, and we need to do things on the past light cone. So for instance, just to give an example, so these, we think that the initial conditions of the universe are very much described by a Gaussian field, but we also know that the best models for the universe are not just exactly Gaussian. They must have these interactions, even if it's just from gravity. So we know that the initial conditions are exactly Gaussian. They're almost Gaussian. So there are known Gaussianities in the initial conditions. To observe these known Gaussianities, we need not only large scales, but we need sort of to map out the large to small scales. We need the lever arm. So connecting large scales to small scales is important. Large scales, if you do the flat sky approximation, you may lose across the line of sight scales, or you may to correct in some way the systematics that are generated because of that. So GR effects also, so general relativistic effects on large-scale structures also in this category here. So what we are doing here is working towards description in very thin redshift cells, so you don't average out everything inside a redshift shell, otherwise you lose the information along the line of sight and between the slices. But the cost is that you end up with having many, many slices. The statistics gets complicated, and you may, and then the analytical calculations here are important. So just to set up the problem, again, what we need are these two-point functions, which are either the correlation function in configuration space or the power spectrum in Fourier space. Of course, we can have all kinds of different traces of large-scale structure, and more people are looking at mapping all kinds of different galaxies, halos, AGNs, groups, clusters, whatever you can find out there. So these two-point functions are symmetric in this sense that I'm writing here. So we have tracer I in a radius r, tracer j in a radius r prime. Of course, this is then symmetric under that transformation where you exchange ir by jr prime. So this is a symmetric object. We need to, our observable, therefore, is a symmetric object, and it's something that we have to keep in mind. When you have many distinct tracers, it turns out that you can describe the inverse covariance of those power spectra in a very simple form. There's an analytical form for that. And the only reason I write you this formula that I don't expect you, for most people here to read into this anything, is that we can figure out actually from this formula here that there is a combination of these observables that you can construct that are completely independent of cosmic variance. What is cosmic variance? Is the fact that when you realize a random field in a finite volume, you have a randomness associated with that. That's cosmic variance, a sample variance in a cosmic arena, basically, right? There are some observables, however, which are independent of this, and this is an idea that goes back to Udo Seljak in 2009, and it turns out that this combination is basically the ratios of these power spectra here that can be measured in principle to arbitrary accuracy. So this is the usefulness of these analytical formulas. They give you an insight about what kinds of degrees of freedom you can construct, how you can get your data, combine it in such a way that you find something, or to understand how something that you thought would not be observable can be observable. Okay, the only problem with the previous formula that I showed you is that usually when we think about two-point functions, we just say, at least in cosmology, we think that when you cross-correlate two different tracers, you think that you just try to use some formula which is basically like this. At least the linear regime, you say that bias is what's driving the difference between your power spectrum and your matter power spectrum. And this means that actually, if you think about it, there are no independent degrees of freedom in the cross-correlations, which is something that people usually assume in one sense or another, but this is sometimes not true, actually, often it's not true. These degrees of freedom can appear, for instance, when you try to describe the structure formation with effective field theories, which is basically the only analytical tool that we have to go beyond the linear regime. But they also can appear physically in terms of environmental effects, things that appear in these cross-correlations, exclusion effects that depend on the type of tracer, and not in other baryonic physics. So actually, the most general case, and this is what I'm going to consider here, it's not crucial for my argument here, but I'll assume that in the general case, we just say that it's a nearly Gaussian two-point function, it's symmetric and it has some noise. This is basically the situation we have in cosmology. I'll not assume that the autocorrelations contain all the physical information. I'll assume that the cross-correlations also contain some physical information here. Okay, so this is the problem here. We have some data covariance. So our data points are these xi. You can think of these as all the positions of galaxies in some redshift slice. And the covariance of that has your signal. So this is the correlation function here. This is your noise. And this is your, what we call data covariance, which is also symmetric here, right? So, well, turns out that you have to eliminate the symmetric degrees of freedom so that you don't overcount, double count these, but this is a trivial issue. And you can actually compute the covariance of that correlation function, which is a trivial formula that most people have seen here. So this is basically a 4-point function, which is given by the Vic theorem by this combination here in the Gaussian approximation. So this is basically data covariance squared, basically. So the covariance of the correlation function is the data covariance squared. It turns out that the exact inverse of this object here is also given by the inverse of the data covariance squared, apart from a first term here, which is a completely trivial formula, which is kind of a, it's underlying many of the formulas that we see out in the textbooks, but you know, this is not very often that you find this in such a simple term, but this is what it is. Okay, so this gives us basically this object here, the Fisher matrix. For those who don't know this, give you the curvature of your likelihood around the maximum. That's what it gives you. So it gives you an idea about how spread out your likelihoods are. So that's a really important formula that you can have here. And it turns out that it's exactly this. So all that you need is to compute, therefore, these inverse data covariance. So again, data covariance is your data points, the covariance of data points, so positions of galaxies. Okay, so all that you need is to invert that. Once you have that, you can substitute it back in the formula here, and you have the Fisher matrix, which is something which is really valuable. Okay, all right. So now, what does it mean? So this is basically up to now. I'm not saying anything new. I'm just writing some formulas here. But what I'm going to tell you about here is how to do that for spherical shells along the past light cone. So basically, we are here, and we are the observer here, and we're looking back, and we see galaxies at different redshifts, at different radii from us. And each one of them, you can think that they are sampling a certain time equals to constant hypersurface here. Okay, so this is let's say, Ti, and this is Tj. And all that we can see is some slice of that time equals to constant hypersurface. So I'm going to be assuming here that these are thin slices for reasons which will become clear later. So you can think that each bin here basically has some width here. So you see some redshift between some value and another value, which is not too distant, okay? And then you're trying to build a statistics that allows you to get the 2-point correlation functions between objects in this slice and objects in that slice, and I want to the covariance of that. So this has also a long history. Okay, many of the things I'll say here are related to that history, but I'll show you also some new formulas which shed some light into this description here, which is, again, the only way to go. There's no other, that's basically it. There's no other way to describe if it's not on the past light cone, because this is what we actually observe. Okay, all right, so again, so you can think that these are galaxies in a given shell here, galaxies in another shell there, and you're correlating them. Of course, once you do that, what you are naturally drawn to is that when you have things on a spherical shell, you want to describe them in terms of a spherical harmonic decomposition, and this is how you decompose that. So this is basically the number counts of galaxies in a given shell. So this is shell counts in shells, if you want. So it turns out that there's a very easy way to compute that if you have a finite number of galaxies in a given shell, for instance. Okay, right. So you can then compute the data covariance of that number counts. So this is the fluctuation in number counts, and you can compute this, and you can actually relate it back to both the power spectrum and the 2-point correlation function, which are in here. Okay, so the signal that we want, so basically the angular power spectrum for 2 redshift slices I and j is related to the 2-point function through this formula here. So what we want to find here is an expression for the Fisher matrix of these guys here for arbitrarily small redshift slices. Okay? Like I told you before, that Fisher, which is the inverse covariance of that object here, is given by basically 2 times inverse data covariance squared. So all that we need is to find a way to express this back into that and then to invert that. So you can imagine that analytically this could be a bit challenging. So first I'll do the calculation in real space to show you that it's actually a very trivial thing to do. You can express the correlation function in this way when you do transform into spherical harmonics. The radial part becomes the spherical Bessel functions. So basically, the data covariance here is given in terms of this simple Fourier integral here. And actually, it's a Fourier-Bessel integral here, okay, of this matrix here, Mij, which is basically the power spectrum here, Pij of k, with the shock noise term, which is this term here. Now, it turns out that it's trivial to invert that expression in a true analytical sense. If you remember that these functions here form an orthogonal basis, an orthogonal radial basis here, and they have this so-called completeness relation, if you want. It's kind of an orthogonality. So it turns out that the exact integral of, the exact inverse of this expression here is this expression there, where this is just the matrix inverse, of that object M, which is this guy here. So trivial to do, very simple. You can show that this is exactly what gives you the inverse of that. So if you multiply that by that, you end up with basically something which is a Kronecker delta for the slices, which is exactly what you need. Okay, so now it's not as simple as that, and up to here, basically, this is not interesting so far. This is something anybody could do, any last year undergraduate or graduate student and first year graduate student in physics working in cosmology could do this calculation here. This is not interesting because there are effects along the line of sight which break isotropy, which are hard to describe, and these are exactly the redshift space distortions.
Oh, you put the harmonic space data dot. This is connected to the degenerate sense. I mean, harmonic space data means something special because the last slide is probably one slide before. I'm just assuming one more.
Here?
The harmonic space data. So the harmonic space, what do you mean by harmonic space?
Harmonic here is spherical harmonics, is LM standing for the angles, basically. So the harmonic basis is both the spherical harmonics in angle,
okay,
and the radial modes are the spherical Bessel function. So that's the harmonic decomposition.
Nothing connected with the degenerate sense of solution, right? So the solution are exactly.
Yeah, so this is a complete basis for expanding some scalar along your let's say your shells. So that's a complete, that gives you a complete description, which is non-singular at the origin.
Yeah,
of course, otherwise you would need the other functions also. But no, this is a complete function for complete series for this field. So radial information is critical here, and the main reason is because we have something called redshift space distortions, which is something which is very easy to see, and if you haven't seen that, if you're not a cosmologist, you can imagine that you have a certain system here which is going away from you. That's the expansion of the universe. That's what we call the Hubble flow. But inside that structure here, you have gravity acting, and you have some sort of a center of mass here, and things are being pulled towards the center of mass through their own gravity. So this guy is falling a little bit that way, this guy is falling that way, this guy is falling that way. So on top of the redshift from the expansion of the universe, you also have a bit of redshift from the what so-called peculiar motions of these galaxies here. And we, of course, don't see the effect across the line of sight, which is order v square over c square effect. We don't see that, but we see the line of sight effect of that in redshift. So v over c gives you an extra delta z on your redshift, and that gets imprinted on all your structures. So whenever you have some structure here in the middle somewhere, you'll see some velocities flowing either towards or away from that mass, okay? And what that does to you is that it breaks the degeneracy now. It breaks the isotropy, because now what you see in redshift, which is the only way that you measure distance, is intrinsically, let's say, polluted, or it carries the imprint of those peculiar velocities here. So this figure here shows you what happens when you are in this so-called linear regime, where these velocities are small. They're just starting to move towards the center. Then when they start to get large, they detach from the Hubble flow. That's what we call the turnaround. And then when they move inside and they collapse, then they create these funny figures here that you're seeing. And this is imprinted. So they break isotropy. We don't see the way that we see things along the line of sight is different than the way that we see things across the line of sight, and it has a bunch of different manifestations here in the data. Okay, so I'll jump straight to the way that mathematically this is manifested in the data. If you fold in this redshift space distortions into our two-point correlation function here, what you have is that you go from the real space description to the redshift space, and that is still in the linear regime, okay? You get these extra terms here, so instead of having just those Bessel functions there in that double Hankel transform that I have there, you get these extra terms, which, by the way, this F here, for those who don't do cosmology, this is basically the rate of growth of structure. That's how fast you are forming structure in the universe, and B is the bias of that tracer. So you get these extra terms here, and then the question is, okay, if you want to do a statistical description of large-scale structure, can you now invert this covariance that comes from that two-point correlation function? And it turns out that you can, and the key for resolving that is actually, because we already have a relation, these two functions here, we already know that they are orthogonal. These other guys here, they are not exactly orthogonal. These are second derivatives, so this is not orthogonal to that, so you have to take each piece at a time. So it turns out that you need to solve some integrals. And as it turns out, some of these integrals, they have exact solutions which are trivial. Of course, all of these integrals here, all of these types of integrals here, just in Fourier space, they can be expressed in terms of hypergeometric functions. But it's completely useless to have a hypergeometric function, because if you put it in a computer, what it will do is that it will try to work out some infinite series that takes forever to work out. There's no way that you can use that, okay? So hypergeometric functions are just a way to throw your hands into the air, say, I give up, and there you go, just take that. Turns out that these integrals here, as we have worked out, by the way, two of the people who worked on this project are here, Ian and João. They helped us to calculate, so you can open these integrals up into a series of terms. It turns out these guys have exact expressions in terms of polynomials. Okay, so we looked everywhere in the literature to find if anybody had written this out. I didn't find anything, at least in the cosmological literature. I also looked in some of the other literature out there. Didn't find anything. I'm sure, however, that some Russian physicists in the 1930s or 40s, they knew about this, because this is all nuclear physics. People in the 30s and 40s, they worked all these things out, but I have no idea what they are. I didn't claim that we have written these for the first time, but in cosmology at least, I think it's the first time that it's written, and it's very useful for reasons that I'll tell you. Okay, so I'm sure that people have worked these out. It's not in Watson's book, it's not in any Bessel function compendium, it's not anywhere, but I'm sure people have worked these out before, because these are trivial. Okay, I mean, not really trivial, but you have to work. I mean, it took us a few weeks, months, something like this, but it's there. Anyway, and why are these useful? Because they give us now a very simple description of the data covariance and basically the correlation function in harmonic space with any kind of radial binning that you want to do. It turns out that you can express exactly the two-point function in configuration space in terms of a kind of a double Fourier transform here, this object here, which is exactly given by the same term that we had before in real space, okay? So this is exactly the same term that we had in real space before. So this is, basically if you put F to 0, you get exactly the configuration space result, but you get an extra term here. So you get a boost here from the growth rate here, the F, but you also get a mixing matrix, which is very interesting. And again, I don't think people have noticed this before, that this is a very simple object, and here it is. It's actually, this mixing matrix is given in terms of those functions that we find as a result of doing those analytical integrals, and they are very much diagonal. They're not exactly diagonal, but they are very much diagonal, and they have these expressions. So for L is equal to 10, and L is equal to 80, this is what they look like. So this is Ki, Kj. These are, let's say, the Hankel transforms of xi and xj, the redshift bins. And if you make cuts here along, say, Ki, what you get is a dependence that falls off very fast from diagonal, actually falls off almost exactly like a straight line here, which is really interesting. So you know exactly how they fall off. So this is basically to tell you that in real space, the mixing of the radii, even with small redshift bins, is some very complicated function, which I'll, by the way, show you later, just so that you can visualize. But in K-space, this is very simple. And it turns out that this is the key here. This guy is almost diagonal. When you get higher L's, this is even more diagonal. So basically, if you look at these cuts here, so as you work your way inside here, so these outer lines here are for L is equal to 10. Then the second line inside here is L is equal to 20, then 40, then 80. So they fall even faster. So in Fourier space, these guys are basically, so again, this is just the purely radial contribution from redshift space distortions to the angular power spectrum. So it's these functions here. So they are almost exactly diagonal. And this is what enables us to go back and describe things in an approximate way, because now, you know, the off-diagonal terms are just a correction. Now you can make basically a perturbative expansion, take the off-diagonal terms, and then you can basically make an analytical calculation from then on. This is, by the way, what you get for the same thing in configuration space. This is a mess, okay? You don't have an analytical formula for this, but this is basically what transforming back from Fourier space to real space gives you. It's a mess. And as you have smaller and smaller redshift slices, it becomes more and more of a mess. And this is just for a single mode, by the way. If you have more modes, it becomes even more of a mess, okay? Of course, you cannot invert this kind of a thing if you have, you know, say if you have 100 by 100 here. Okay, there's no way you will invert something like this. I mean, you would need a huge amount of, that's just for 1L, by the way. So with thin slices, there are many, many more values here. Remember that the correlation function gives you, so you can think of this. Imagine that what you want to do as somebody who is trying to connect theory with observations is that you want to map out each point of this matrix here. So if you have 100 redshift slices, this is 10 to the 4 divided by 2 points that you need to map out. So this is your observable, these 10 to the 4 points, basically. And you need to know the covariance of those 10 to the 4 points with all the other 10 to the 4 points. Think about this as a numerical problem, and you immediately realize that it's hopeless, right? You would need millions and millions of simulations, which of course you don't necessarily want to do. So the problem is that we want to have the thin redshift slices because we want to keep the information along the line of sight. Otherwise, you smear out the redshift space distortions. You lose information. You don't want to do that. But the cost for that is that your problem becomes of a huge, huge order. Of course, you cannot deal with such a huge dimensional problem with numerical stuff, but you can with analytical approximations. That's exactly what they are there for. So what I want to do here is that I want to consider the case where you have many, many redshift slices, and you have the the angular power spectrum for very, very thin redshift slices, and I'll show you the formula for the covariance of those guys, okay? By the way, these kinds of objects will not be diagonal at all, but they'll have a structure that we can resolve analytically. This is, by the way, here, what you get for the covariance of the angular correlation function in thin redshift slices. How many redshift slices did we use in this exercise again? Do you remember? 40, 25, 25. This is just with 25 redshift slices. This is the kind of covariance that you have. And if you want a Fisher, you would have to invert that. Good luck with that. That's just 25 redshift slices. Of course, you want more than that, because you can imagine that if you have a spectroscopic survey, you can have hundreds, maybe even thousands of redshift slices. So this is the covariance, just for L is equal to 10. So this is what we have computed in a sort of simplified model in theory. This is also what we simulated here with, I don't know, João, how many simulations did you have to use? Thousands and thousands and thousands of simulations, right, just to have this. And this is a very simple model that, by the way, has a nearly analytical expression here. So I just submit to anybody that has ever work with data that if you want to use some covariance matrix like this, it might present a challenge, right? So how do you solve for this? Well, you go back to the expressions that we had before. So basically, this is the data covariance that has your, take the hand out of here, has the off-diagonal terms in here. So you can rewrite this as a purely diagonal object plus some off-diagonal terms. Then you can plug it back in, and you can write the expression for the inverse as a perturbation series like this. So it has shot noise. It has diagonal term in Fourier space. And then it has the first corrections from the off-diagonal terms, which are in here. They depend on this guy here. But these are all simple expressions. They are, the only trouble here are these Fourier integrals here, which we have calculated using codes called FFT log, which compute very fast integrals involving these Bessel functions. It turns out that even these integrals here you can solve within a matter of seconds, even these Fourier integrals here, the double Fourier integrals here. Okay, so just to give you some background, if you wanted to compute this here on the basis of simulations, you would need an absolutely humongous amount of computing power, not only to compute to make all these realizations of your maps, but also to compute the covariance. You need to keep up a huge amount of data in your computer. So this is basically doing this even with Flask or Glass, impossible. There's no way that you can do this with more than, I don't know, I don't remember. Artur is the guy, Artur Loureiro, our other collaborator, is the guy who gave us the number, but I think it's with more than 15 or 12 slices or something like this. It's just impossible to do with Flask or even the new version, which is called Glass, which I think they are about to release. But you can do this analytically in the linear approximation. So basically, once you compute that with that formula that I just gave you, which is, again, a matter of seconds or minutes if you want to have L from, say, 4 until 100, okay? So this is what you compute here. You plug that back in, and you have a Fisher matrix. And then you can do everything that you do with Fisher matrix. For instance, in power spectrum, you can plug it back in a Fisher code, or you can plug it back in a Monte Carlo, whatever you want to do. So what we assume here is Gaussianity, linear regime, and full sky. Full sky is not so important because you can actually have partial sky, use pseudo-CLs, and then there's a mixing. You can make bins and Ls, and that's pretty much the same thing. You treat a bin and L just like an L. It doesn't matter too much. But these two are key assumptions. However, if you think about any Fisher calculation that you've ever done in your life, you assume that anyway, so that's not a really critical assumption here. I mean, at least not different from what we usually do. And also already gives you a first step if you want to correct for some nonlinear stuff with starting with an analytical formula.
So linear is because you use the linear power spectrum, that's all?
Yeah, I'm using redshift space distortions in the linear regime. Okay? It's an interesting question about what if you can fold into your model some nonlinear redshift space distortion model. Beyond Kaiser. I don't know. I haven't done the calculation, but it might be possible. I don't know, but I don't know about that. Okay, so basically, this is a simple and straightforward. It doesn't look that simple, but given a certain model, which you always have to provide a fiducial model there, the integrals are actually straightforward with the present tools that we have. So the question is, to what accuracy do we need these? Can we somehow use the Lieber approximation to simplify those integrals?
Like Lieber. If you look at the approximations there, the first term with the delta function looks like Lieber.
Yeah, so the second term would be beyond Limber in some sense, but it's beyond Limber. Yeah, it's something like this, but it's, yeah. So maybe the second one you can approximate with Limber because they also have these integrals in there. Yeah, that's basically the idea. That would be to make it even faster. Anyway, so the question is then how we now go to some nonlinear scales, how we incorporate other effects like lensing and other things, which I'm not very optimistic about how we can incorporate effects which are integrated along the line of sight, because then these lead to complicated radial integrals that kind of Not sure. I'm not sure about this. We are looking into this, but I'm not very sure if we can do this effectively. Okay, so what is next here? Question is, why would somebody use something like this? I mean, why do you care? Why have you made this calculation? First of all, I've made this calculation because it's possible. and eventually, if you have an analytical description, somebody will use it eventually, because it has to be there, and it's the basis for anything else. So anyway, so there it is. Now, it may be useful in the following sense. When we are now more and more trying to observe large-scale effects like non-Gaussianities, like GR effects, testing gravity on larger scales, etc., we need to go to connect both the large scales and small scales. If you just smear things out along the line of sight, you're losing information, you're losing small-scale information. It's not clear to me that you're going to get as good constraints that you could have. And it's not clear to me that you would not be biasing your evaluations if you're just assuming that you have no, if you just put a box in there, you assume that there's no time evolution. It's unclear. So the next step, and this is the project of one of my students here, João, is to calculate, to have a very nice toy model where we can both do the complete parameter estimation both in Fourier space and in harmonic space to map out the ways in which you delimit the problem. So small scales, everybody knows that the small scales you have to eventually cut off from your problem. You have to put some limits to how much on small scales you can go. When you have Fourier description and harmonic description, small scale means something different, right? But there's a way to map these two problems, and then we can compare, and we can see if our parameters are equally well estimated in both approaches, and if there are no significant biases in them that appear as a result of imposing Fourier or not. Before, this calculation would be impossible. Now that we have an analytical Fisher matrix, it's possible. At least we can figure out if there is relevant information in a harmonic description, which is lost when we go to Fourier space. May very well be that there is none, and we're just making a lot of trouble. But this is the question here. So how does the harmonic description compare to Fourier space? So this is basically the next step here. Okay, now for the second part of my talk, which may be more fun for many people here, which is using machine learning to do a lot of stuff that we like to do and we don't have the patience to do if we don't have infinite time to sit on our problems. So more and more people are using this. Actually, as far as I understand physics and astronomy, there were some early papers in the end of the 90s, I think, beginning of the 90s actually, but it wasn't really adopted a lot, and I think physics and astronomy are a bit of a latecomers for this. Actually, in many other areas, people have used this a lot, but physics and astronomy is only in the past, I don't know, 4 or 5 years that it's exploded, and now everybody's trying to do everything with that. I'll give you some examples of what you can do here. So this is actually connected with the question to Thaisa earlier on. We have these simulations where you have dark matter and baryon physics, and you have galaxies emerging out of those simulations. It turns out that to a very good extent, you can just use the dark matter information to predict the properties of the galaxies that will form in a given dark matter halo. It turns out that if using these machine learning methods, which are really good for tackling these very complex problems with hundreds of variables, highly nonlinear relations that you couldn't possibly describe in an analytical sense, you can train certain code to use the information about the dark matter to predict the properties of the galaxies. And to a good extent, this is what people are being able to do. So in some sense, to a number of properties of the galaxies that you have in your volume there, you may not need full hydro simulations if you have a large enough sample of simulations that you can train. Then you just give some dark matter simulation, and then you paint on the galaxies. There are many models that people have used since forever for this, like models and so on, but machine learning does this much better than all the codes that have done before. The only problem is, like the question for Thaisa, is that on these models here, the way in which the simulations, the hydro simulations, implement baryon physics is imperfect, and they assume some small-scale effects, which we don't really know, actually. So there are some unknown physics going on. You can train with different kinds of models for the baryon physics, and out come slightly different types of galaxies. You can kind of smooth out these things and introduce some error because of that. So this is a paper with my students Nathalie and Natalia that predict properties of the galaxy. So the true properties are here in the contours, and the predicted properties are here on the color lines here. Another thing that we have played with is this, the notion that machine learning is a black box. So anybody has, by the way, let me make a kind of a poll here. Who here has played with machine learning in any sense? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So this is mostly, I would say, more of a theory-oriented crowd, right? So that's a lot of people, right? Okay, so if you have ever thought about this, looked at how these machine learning codes work, they are a completely black box. Forget about understanding what goes on inside. That's totally beside the point. The output of a machine learning code is, let's say you want to classify objects. You give pictures of cats and dogs. You want to say, is this a cat, is this a dog? It gives you a score. This is a score of 0.8 for being a dog. This is a score of 0.9 for being a cat, or something like this. Now, what is a score? Score is something that's spewed out from the code. It's not a probability. It will never be a probability. It has not the sense of a probability. Now, how do we as physicists work with something which has no sense of being a probability? How do we deal with that? What is the probability of something that I'm observing here in my data, that it's a galaxy, star, that's a quasar? If all that you give me is a score, how can I then fold that into the information that I have? Because it's in the basis there, right? So there is a connection which is very, very far from trivial between machine learning outputs and probabilities. It turns out that for almost all of the machine learning community, errors do not exist. There are no errors. People just give, what is your height? It's 180. 180 exactly, 180,000. They just write that. There's no errors anywhere. Or they assume that the errors are all the same for all the data points that you have. A lot of machine learning, I would say 99.9% of all machine learning literature is based on the assumption that your data is categorical. There's no error. Okay? Now, it turns out that errors, of course, are on the basis of any statement that you do about signal and noise, and therefore of the relevance of the data points. And we've done here a quick study of how including the errors make your whole machine learning code work better. So it turns out that machine learning codes, they can be tuned to return you something which is almost a probability. So you train them to see probability, even if they have no sense of what a probability is. But for that, you need to give data to the machine learning which has errors. Otherwise, how would it learn about the errors? That is a basic point. But it's very much lost in much of the machine learning literature. And we, in this paper here, showed how when you include errors, basically you turn the scores of the machine learning into basically a one-to-one function that's related to probability. So they can be mapped to probability. In the absence of errors, basically, you have zero correlation. And your score is anything. All right? So if you're just doing some task with machine learning and you think your score is a probability and you're assuming that, look at this figure. So this is the true probability, which is calculated with a Monte Carlo. And this is the actual, let's say, score of your machine learning. It has no relation. It's just completely unrelated to that. So if you want to have a sense of probability, the basis of that is in the measurement, is in the input data. If you don't have any errors in the input data, there is no probability anywhere. It's not in the beginning, it's not in the end, it's nowhere. Well, finally, just how many? I have 0 minutes, I guess, right?
No, 4.
Okay, so that's time enough. Another application that we have done here is, again, going back to the covariance matrices. So basically what we have here is that in large-scale structure, true simulations that actually reproduce your structure formation in all scales or even without baryon physics are extremely expensive, okay? If you want to simulate a cosmological volume on scales small enough to resolve even, let's say, a group, individual subhalos in a halo, you need an n-body simulation, which is hugely expensive. So if you want to have your observables and you want to give a sense of the covariance of those observables, so the probability, you need many simulations. Now, typically we need to compute, if you're just doing the simplest thing you have, which is power spectrum in Fourier space, which has a nearly covariance, nearly diagonal covariance, what you get here with, let's say, 50 cosmological volume simulations is something which is as noisy as what I'm showing here to you. And you need to know that very well, okay? So how do you do that? So we had this idea here with my student Nathalie that we could actually use the generalization power of machine learning to teach a certain code to denoise covariance matrices. So basically what we have done here is that we use cheap simulations, what we call mock generators, to teach the machine learning code how to clean this covariance matrix so that it becomes equivalent to the covariance matrix that's produced with thousands of simulations. And then we apply that same code to a covariance matrix that's produced with very expensive n-body simulations. So basically here we used Cola type mocks to train the code, and we apply to the Pinocchio simulations, which is basically the only simulation we have out there in the universe that has literally thousands of n-body simulations for the same volumes. So we know what to expect from this when we clean it up. We know what the result here has to be. And it turns out that machine learning is incredibly accurate at doing that. So you start with here, so this is a measure of, n here is your sample size. And here is a measure of your noise. Let's say this is your residue. So it's the level of noise in your covariance matrix. So of course, when you have very small samples here, have very high noise, as your sample increases, your noise level goes down. So when you apply this denoiser, which is basically an encoder, you lower the noise level here, and a sample which has about 50 maps, 50 volumes, becomes as good as a sample that contains about 500 simulations. And when you have more, this becomes 800, 700, 1,000. So you can basically, with very little cost, get something which is, for the price of 50 simulations, you can get something which has basically is like 500. Something else that you can do with machine learning. Of course, these things have to be tested to death, otherwise you might very well be doing some crazy stuff to your covariance matrices. But this is, again, on the basis of pretty much anything that we do in cosmology, because covariance matrix is what you feed to your Monte Carlos, is how you fit parameters in the end. So having a less noisy covariance matrix is critical. And here are some figures that we have done here in this paper that show you how a sample of 100 simulations here gives you some bias in some parameters like omega c, like the bias and other parameters. And when you denoise that, you get basically back the exact parameters that you would have with a much, much larger sample size. So again, that shows you that the machine learning is not biasing is not introducing, it's not skewing your covariance. It's not introducing spurious structures in your covariance. Okay, so I'll stop there because these are conclusions. I'll probably just go for the questions. Thanks.
Hello, thank you for your talk. 2 questions. I don't think they're very hard to answer. The first one is, you mentioned how for low L's, the Fisher matrix stops being nearly diagonal. At least they stop. The approximation is not very good. Does this have anything to do with cosmic variance?
for low L's, not sure. I'm not sure. I haven't thought about this actually.
Because
For low L's, you are averaging out an angle over big
larger
volume,
structures,
so
right?
it's like you're correlating larger distances. So you expect things to be more correlated inside a given volume because you're averaging out over larger distances anyway. But in the end, it's a bit like this. You're talking, what is the size of your volume is the size of your shell, right? So for lower L's, you are averaging out bigger chunks of your 2D sphere. So in some sense, things are more correlated. So that's pretty much the same as cosmic variance in some sense. You have more variance for the long wavelength modes if you want. So yeah, probably it's the same thing. Probably it's the same statement, although I haven't thought about that. Thank you for the, for the thought.
Thank you. And the second one, when you mentioned when you include the first order corrections to the line of sight and the radial functions for the redshift space, yeah. Where we have the derivative of the spherical Bessel functions. Yeah, exactly, perfectly. Do these HL and GL functions have anything to do with the green functions of these?
The what?
The green functions of these JL and their derivatives? Because
well, in some sense, what you're doing is you are, you can think of each redshift slice as an impulse in that sense, right? So you are, I guess in a very broad sense, you can say that this would be kind of if you integrate over these functions with the redshift cells, what you get is the covariance. So in some sense, maybe, but I wouldn't go as far as that because we don't really have a second order equation, linear equation that we're solving in a usual sense. So it's not, although the interpretation is similar, right? Yes.
Okay,
yeah.
Thank you.
Thanks. So all of this, the derivation here is for infinitesimally thin redshift shells, is that right?
It's for very thin shells, yeah.
If one wanted to do this calculation for redshift shells that had some width, does this formalism, like, is there a way to extend this?
Yeah. No, the calculation in the paper is for finite shells. All that you need is that you assume that there is no evolution within each shell. If there is evolution within the shell, then the calculation doesn't work. But all the formulas in the paper, this is simplified for a presentation. But on the paper, it's all for finite shells of a finite width. So there's a volume, there's a radial bin width. But they only work if you assume that within the shell there's no evolution. So all the quantities within the shell are at a time equals to constant hypersurface effectively. Yeah.
Thanks.
Okay, very interesting talk. I have a question. In your treatment of distortions, have you also considered Alko-Paczynski distortions, or they are not significant?
Well, this is kind of this is not a angular distance versus luminosity distance question, really. But they are all in the same category of things that break isotropy in some sense, right? Yes. So if you look at this, figure here, you can think about this in the radio and across the line of sight as a kind of an Alko-Paczynski, because the way that you measure these structures here, which are the BAL scales, is that you can think of angular and radial. The way that you measure them is intrinsically different because you're using a sort of a angular distance and radial distance, and this is kind of an Alko-Paczynski. In the sense that I'm telling here, no, this is just the effect of peculiar velocities, okay, and the projection of that. No, I would say that it's a simpler case.
Okay, thank you.
I mean, that's my interpretation. I don't know about you guys, if you think that there's I mean, people call many things Alko-Paczynski. I don't know. Sometimes it gets a bit fuzzy. Yeah.
Yeah. Thanks, Raul. Really nice talk. I I should probably look at the paper, but the last thing that on the second part of your talk, when you showed this figure with the MSA, which is I think the mean square error of the associated with the covariance matrix, probably.
Yeah.
Okay, that's one thing. The other thing is you showed the Wishart analytical computation.
Yeah, I didn't say anything about that. That's the, yeah.
No problem, no problem.
If
Yeah,
you want, I can explain now. Now that you asked, I have to explain.
My curiosity is why the points are always above the Wishart?
Yeah.
There's a...
So what you're seeing there is the expectation value and the 1 sigma width around Wishart, right? So I think that, you know, we're actually doing a kind of a, I think 1 gigaparsec volume, computing the power spectrum inside, so there are many other effects in there. I'm not sure that the Wishart is for a certain Wishart formula. So Wishart is a kind of a PDF for a covariance matrix, assuming, making a lot of assumptions. And I'm not entirely sure that all the assumptions are true for the power spectrum that we are computing on the basis of really simulating something, measuring the modes with some band powers and so on. And it's not clear that all the assumptions are true. So maybe the fact that we get a bit higher is reflecting that. But it's like 1/3 of sigma away from that. So I don't know how significant that is. Yeah, so just for you guys to understand, so the gray line is an analytical formula called the Wishart distribution. By the way, Elaine, who would be here, is the specialist in the world about that. And it's, anyway, she corrected some of the stuff in the literature about this. So yeah, so that's just to, that curve there is just to give you an idea of how you would be effectively enlarging the sample by using machine learning to clean out the covariance matrix. That would be effectively augmenting the sample.
It's really nice.
That's basically it. It just serves that purpose. It's not really, it's just to guide your eye in some sense.
Right. It's super nice.
Yeah.
And then I should begin with this question. You are denoising the covariance matrix.
Yes, the
you are not
covariance
doing that
directly.
on the precision matrix. You are doing that directly on the covariance, not in the inverse of the covariance.
No, I'm doing that in the covariance because that's what you compute to start with before you do anything like precision or anything like that, right? I mean, I would say that cleaning out the covariance is much safer than computing a precision and then cleaning out that, because if you compute the precision from an inaccurate covariance, then you have already introduced some nasty stuff in your problem. I would think that this is, I don't know, that's a good question, but I would say that I would be very surprised if working in the precision matrix would be better than working on the covariance and then working away later to the precision. And by the way, this is basically here, this is a manifestation of the precision matrix, right? Yeah. Right? So this is the precision matrix in practice after you put that in your Monte Carlo. Yeah.
So I have a question dovetailing this last one. So it's a provocative question. It's a bit long, so let me just describe it a little bit.
I'll sit down.
So in numerical simulations, so people, depending on which camp, will present the result as if this is correct because it looks right. Other camps don't have the luxury of dealing with fields that naturally have an interpretation. Well, so it's hard to say it looks right. So you have to go work hard to show the error is this, and this is why we trust the solution. So in the context of machine learning, we're starting to grapple with this. So I always point to, and I think those of us that have worked in one way or another in machine learning have this challenge in front of us. So I typically send students that want to do numerical simulations, say, well, go open the book by J.P. Boyd. It's in Spectral Methods, and look at definition 16. It's either 16 or 17, depending on which edition. It's a pretty cool book, has lots of interesting snippets here and there, but definition 16 or 17 is the definition of an idiot.
For what?
An idiot. And it goes basically, an idiot is someone that presents a numerical result without having done A, B, and C, right? And that's very good because it tells you at the end of the day, this is the error that this particular simulation would have. So we need a definition of an idiot in machine learning. Do you have one?
Definition of an idiot.
Yes. If you publish a result, so what you typically see is we've trained with this many sample sets. This is the result. Okay, how do we know we should trust it? To what degree? So you're going after it with this.
I have an exact definition of that. If you don't know, if you cannot even tell the difference between a machine learning score and a probability, then you're an idiot. If you don't know how the uncertainties in your data, in your method, or in your model, or in your theory, how that propagates your uncertainties in the end, then you are an idiot. And I would say that this is the beginning only, right? And if you don't test to death the end result with all the ways that you can measure how some black box is skewing or biasing your result, then again, you are an idiot. I would say that there are multifold ways of being an idiot, but it starts with realizing that machine learning is a black box, and that, however, that it will be more of a black box if you hide from it the uncertainties in all your assumptions and your data. So just the fact that more than 99% of the machine learning community doesn't even consider that errors exist means that there's something wrong. Of course, for many things, these are categorical things, right? It's 1 or 0, exist, do not exist. So how much money you have in the bank, it doesn't have an error, that, right? But, I mean, everything else is uncertain, including the model that you're using, including the many assumptions that you are kind of building into your system. So, I mean, there's no way around it. So if you want to do any kind of a science-like prediction in the end that carries a certain weight of certainty, you wanna make a discovery, it's 5 sigma. Okay, I don't have an idea what a sigma is. Then you don't have a discovery, right?
Thank you.
I hope I'm not an idiot, but I'm not sure.
That was very clear. Okay, one very last question before coffee. So be quick, because you're keeping us from coffee.
No pressure.
So thanks for the talk. In the second part, where you talked about machine learning, at some point you showed the score prediction versus a real simulation. And I did not actually, and you presented, you said the errors, introducing errors actually fixes this problem, but I did not actually understood the moving parts of this experiment. Could you?
Okay, so it's very simple.
Okay.
We have curves here, which is basically a parabola, okay, and it's either up or down. This is actually called the smiley, frowny model here. And your points here, they are representing measurements. Yeah. Some measurements have small error bars. Some measurements have higher error bars. Okay. There's no way, if you don't tell them, if you just put the points there in the machine, it has no idea which points are relevant, which are not. Okay? There's no way that it can infer from anything. So you're making the black box even more black, even more opaque. Okay. So we have a kind of a Gaussian distribution for pretty much everything in here, both all the parameters. So we know exactly, actually it's an exactly integral model. We can compute analytically the Fisher matrix in this case. That's another good thing here. So we know exactly what these probabilities are, but we can also do a Monte Carlo calculation for the likelihood that an object is of type A or type B, if you want. Okay. So this is the Monte Carlo here, which is an exact posterior in that sense. Okay, we control everything in the system. Okay. And we compute also the machine learning confidence here in a variety of methods when we do not include the error bars and when we include the error bars. It's still a black box, but the black box without the error bars is incapable of inferring what is anything like a probability, whereas when you give the error bars, you get this. You get it's not a line, but it's a one-to-one relation that can be mapped. Here, it's not in any sense a curve. In this case, it is a curve. So it's a sort of a nonlinear transformation that given one, you give the other. In this case, it's impossible without feeding the errors into the system.
So the errors are actually fed into the machine.
Yeah. So here in this case, you just give the points without the error bars, and in these two, in this other case here, you give the errors together with the points. So you feed into the machine learning the points, data points with the errors. And it's slightly more complicated how to do that, but you can do this. And since it's a very simple system with basically a Gaussian realization, we could do zillions of these things. So we have a very good, we can map these figures to exquisite accuracy, and so we can say, okay, now a relationship emerges that wasn't there before. But it doesn't matter how many simulations you have, it doesn't matter how you augment your data set, it doesn't matter what to do. If you don't tell the system what your errors are, it cannot infer that. It's just as simple, it's obvious. Anybody has, first year student in physics knows this, right? If there's no sense of uncertainty in your measurements, then whatever conclusions you have in the end, they have, I mean, what kind of a meaning do they have? They have zero meaning, right? It's as simple as that. But amazingly, the vast majority of machine learning community doesn't even think about errors. They don't exist. Maybe for good reasons, but often for very bad reasons. They just used to doing things like this.
Thank you.
But yeah, I'm not, by the way, the only person who has done this. Many people have used this, even in astrophysics. But it's very far from the norm.
Okay. I was interested about the architecture of the machine learning. How do you?
I can tell you. Yeah.
Okay.
Okay.
So
I've abused your time. Thank you.